According to the National Electrical Code, specifically Article 409.21, the overcurrent protection device, or OCT, within a control panel must be sized exclusively on the basis of the loads that are physically installed and operational at the time of installation. This regulation explicitly excludes the consideration of future loads, irrespective of their anticipated addition or operational timeline. The implications of this requirement are significant for control panel design and installation practices, as it ensures that the OCT is appropriately matched to the immediate demands of the connected equipment, preventing both underprotection and nuisance tripping. The primary rationale behind this stipulation is to maintain a safe and reliable electrical system. Overcurrent protection devices are designed to protect electrical circuits and equipment from excessive current flow, which can result from overloads, short circuits, or ground faults. If an OCT is sized based on future loads that are not yet present, it will be too large for the actual current draw of the initially installed equipment. This can lead to a situation where a genuine overload or fault condition goes undetected, potentially causing damage to the equipment or even posing a fire hazard. Conversely, attempting to accommodate future loads by significantly oversizing the OCT can also lead to nuisance tripping when the system operates under normal conditions with the initial loads. This can disrupt operations and create unnecessary downtime. To ensure compliance with NEC Article 409.21, the following steps should be taken. Firstly, accurately determine the full load currents, or FLC, of all motors and other apparatus that are installed within the control panel at the time of installation. This involves consulting the nameplates of the equipment, which typically provide the FLC rating. If the nameplate information is not available, refer to the appropriate tables in the NEC, such as those found in Article 430 for motors, to determine the FLC based on the equipment's horsepower and voltage rating. Secondly, calculate the total current draw of all connected loads by summing the individual FLC values. This calculation should include all motors, transformers, power supplies, and any other electrical devices that will be operating simultaneously. It is crucial to consider any diversity factors that may apply, which account for the fact that not all loads will be operating at their full rated current at the same time. However, it is important to exercise caution when applying diversity factors, as overestimating the diversity can lead to undersized OCT protection. Thirdly, select an OCT with an ampacity that is sufficient to carry the total calculated current draw, while also providing adequate protection against overloads and short circuits. The NEC provides specific guidance on selecting the appropriate OCT size based on the type of load and the conductor ampacity. For motor circuits, for example, the OCT must typically have an ampacity of not more than 175% of the motor's FLC for inverse time circuit breakers or 225% for fuses, as specified in NEC Article 430.52. Fourthly, document all calculations and assumptions made in the OCT sizing process. This documentation should include the FLC of each load, the total calculated current draw, the selected OCT ampacity, and the basis for the OCT selection. This documentation will be valuable for future reference and will facilitate compliance with inspection requirements. Now consider a practical example. Suppose a control panel contains the following loads: one 10 horsepower motor with a full load current of 28 amps at 460 volts, a 5 horsepower motor with a full load current of 15 amps at 460 volts, a 1 kilovolt amps transformer with a primary current of 2.4 amps at 460 volts, and a power supply with a current draw of 5 amps at 120 volts. To determine the appropriate OCT size, firstly, calculate the total current draw. The total current draw is 28 amps plus 15 amps plus 2.4 amps plus 5 amps, which equals 50.4 amps. Secondly, select an OCT with an ampacity that is sufficient to carry 50.4 amps, while also providing adequate protection against overloads and short circuits. According to NEC Article 430.52, the OCT for a motor circuit must typically have an ampacity of not more than 175% of the motor's FLC for inverse time circuit breakers. In this case, the largest motor is the 10 horsepower motor with an FLC of 28 amps, so the maximum optimum capacity for that motor is 28 amps times 1.75, which equals 49 amps. However, since the total current draw of all loads is 50.4 amps, the OCP must be sized to carry at least that amount of current. Therefore, a 60 amp circuit breaker would be an appropriate selection in this case. It is important to note that this is a simplified example, and the actual OCP sizing process may be more complex depending on the specific loads and the requirements of the NEC. It is always recommended to consult with a qualified electrical engineer or electrician to ensure that the OCP is properly sized and installed. Now consider the implications of including future loads in the OCP calculation, as the customer has suggested. If the customer intends to add 2 additional motors to the control panel in the future, and these motors have a combined FLC of 30 amps, the customer might be tempted to size the OCP based on a total current draw of 80.4 amps, which is the sum of the current loads of 50.4 amps and the future loads of 30 amps. However, this would violate NEC Article 409.21, as the OCP must be sized based only on the actual loads installed at the time of installation. If the OCP is sized at 80 amps to accommodate the future loads, it would be too large for the initial current draw of 50.4 amps. This could lead to a situation where an overload of, say, 65 amps goes undetected, as the 80 amp OCP would not trip until the current exceeds 80 amps. This could potentially damage the equipment or create a fire hazard. Furthermore, even if the OCP is sized to provide adequate protection for the initial loads, it may not be properly coordinated with the other protective devices in the electrical system. Coordination refers to the selective tripping of overcurrent protection devices, where the device closest to the fault trips first, minimizing the impact on the rest of the system. If the OCP in the control panel is oversized to accommodate future loads, it may not trip quickly enough to prevent damage to the upstream protective devices or the electrical distribution system. To properly address the customer's concerns about future loads, several options can be considered. Firstly, install a separate control panel for the future loads. This would allow the OCP in the original control panel to be sized based only on the actual loads installed at the time of installation, while the OCP in the separate control panel would be sized based on the future loads. This approach would ensure compliance with NEC Article 409.21 and provide adequate protection for all equipment. Secondly, install a larger control panel with sufficient capacity to accommodate the future loads. This would allow the OCP to be sized based on the total current draw of all loads, including the future loads, but only after the future loads are actually installed. In the meantime, the OCP could be sized based on the initial loads, and then replaced with a larger OCP when the future loads are added. This approach would require careful planning and coordination to ensure that the OCP is properly sized at all times. Thirdly, use a current limiting OCP. Current limiting OCPs are designed to limit the amount of current that flows during a short circuit or ground fault. This can help to protect equipment from damage and reduce the risk of fire. Current limiting OCPs can be used to provide additional protection for the initial loads, even if the OCP is sized to accommodate future loads. In summary, NEC Article 409.21 prohibits including future loads when sizing the OCP in a control panel. The OCP must be sized based on the actual loads that are installed at the time of installation. To ensure compliance with this requirement, accurately determine the FLC of all connected loads, calculate the total current draw, select an OCP with an appropriate ampacity, and document all calculations and assumptions. If the customer is concerned about future loads, consider installing a separate control panel, installing a larger control panel, or using a current limiting OCP. Always consult with a qualified electrical engineer or electrician to ensure that the OCP is properly sized and installed. Now let's discuss the potential consequences of misinterpreting or disregarding NEC Article 409.21. There are several risks associated with failing to properly size the OCP in a control panel based on the actual installed loads. Firstly, inadequate protection of equipment. If the OCP is oversized to accommodate future loads, it may not trip quickly enough to protect the existing equipment from overloads or short circuits. This can lead to damage to motors, transformers, and other electrical devices, resulting in costly repairs or replacements. Secondly, increased risk of fire. An oversized opt may not interrupt the flow of current quickly enough to prevent a fire in the event of a short circuit or ground fault. This can pose a serious safety hazard to personnel and property. Thirdly, non-compliance with electrical codes. Failure to comply with NEC Article 409.21 can result in fines, penalties, and project delays. Electrical inspectors are responsible for ensuring that all electrical installations meet the requirements of the NEC, and they may require corrections or modifications if the opt is not properly sized. Fourthly, voided warranties. Some equipment manufacturers may void the warranty if the opt is not properly sized, as this can indicate that the equipment was not installed in accordance with the manufacturer's instructions or the requirements of the NEC. Fifthly, increased insurance premiums. Insurance companies may increase premiums or deny coverage if the electrical system is not properly installed or maintained, including the opt sizing. This is because an improperly sized opt can increase the risk of electrical fires and other hazards. To avoid these consequences, it is essential to have a thorough understanding of NEC Article 409.21 and to follow the proper procedures for sizing the opt in a control panel. This includes accurately determining the FLC of all connected loads, calculating the total current draw, selecting an opt with an appropriate ampacity, and documenting all calculations and assumptions. It is also important to stay up to date with the latest revisions of the NEC, as the requirements for opt sizing may change over time. In addition to the specific requirements of NEC Article 409.21, there are several other factors to consider when sizing the opt in a control panel. Firstly, the ambient temperature. The ampacity of conductors and opts is affected by the ambient temperature in which they are installed. If the ambient temperature is high, the ampacity of the conductors and opts may need to be deaerated to prevent overheating. NEC Table 310.15 provides guidance on deaerating conductor ampacity based on ambient temperature. Secondly, the altitude. The altitude at which the control panel is installed can also affect the ampacity of conductors and opts. At higher altitudes, the air is thinner, which reduces the cooling effect of the air. This may require deaerating the ampacity of the conductors and opts. Thirdly, the type of load. The type of load connected to the control panel can also affect the opt sizing. For example, motor loads typically require a larger opt than resistive loads due to the inrush current that occurs when the motor starts. NEC Article 430 provides specific guidance on sizing opts for motor circuits. Fourthly, the interrupting rating. The interrupting rating of the opt is the maximum amount of current that the opt can safely interrupt without failing. The interrupting rating must be sufficient to handle the available fault current at the point of installation. The available fault current can be determined through a fault current study, which is typically performed by a qualified electrical engineer. Fifthly, the coordination with other protective devices. As mentioned earlier, the opt in the control panel should be coordinated with the other protective devices in the electrical system to ensure selective tripping. This means that the opt closest to the fault should trip first, minimizing the impact on the rest of the system. Coordination studies can be performed to determine the appropriate time current characteristics of the opts. Sixthly, the listing and labeling requirements. All opts used in control panels must be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or all. The listing and labeling indicate that the opt has been tested and meets the applicable safety standards. In addition to these factors, it is also important to consider the specific requirements of the equipment being protected by the opt. The equipment manufacturer may provide specific recommendations for opt sizing, and these recommendations should be followed whenever possible. Furthermore, it is important to consider any applicable local codes or regulations that may impose additional requirements for opt sizing. Local codes and regulations may vary from the NEC, so it is essential to be aware of these differences and to comply with the most stringent requirements. To ensure that the opt in a control panel is properly sized and installed, It is recommended to work with a qualified electrical engineer or electrician who has experience in control panel design and installation. A qualified professional can assess the specific requirements of the application, perform the necessary calculations, select the appropriate opt, and ensure that the installation complies with all applicable codes and regulations. In conclusion, NEC Article 409.21 is a critical requirement for ensuring the safety and reliability of control panel installations. By understanding and complying with this requirement, it is possible to prevent equipment damage, reduce the risk of fire, avoid code violations, and maintain the integrity of the electrical system. Remember to always size the OCPD based on the actual loads installed at the time of installation, and to consider all relevant factors such as ambient temperature, altitude, load type, interrupting rating coordination, and listing and labeling requirements. When in doubt, consult with a qualified electrical professional to ensure that the OCPD is properly sized and installed.